Yeah, let's start with an observation today. Let's work on a problem. So here's what we're going to do. We're going to take a point. Well, we have a circle. I'm going to take a point that doesn't live on the circle. So let P be a point It is the best when you get a nice clean board in the morning with no dust on it or anything. I love this so much. Anyway, let P be a point not on a given circle C. And what we'll do is we'll draw any line through P. Draw any line through P. So I'm gonna draw this line so that it actually intersects a circle. And we'll look at the 2 points of intersection. So draw any line through P that intersects C. At 2 points that we'll say are X and Y. At points X and Y. Alright, so we have this circle. I've chosen a point P. Choose this point P that doesn't live on the circle. And then we'll just draw any old line through P that we want. Alright, so draw any old line. Line going through P. Then meets the circle in 2 points, X and Y. X and Y. Any objections to this picture? Does this match up with what I've said?
You could be outside the circle.
Yeah, it could also be outside the circle, right? So we'll call this case 1. This is the case where it's inside the circle. And we'll talk about the other case in just a second. And so be careful what's specified and what you can assume based on that. And it just says let P be a point not on the circle, so it could be inside or outside. And what I'm going to do is I'm just going to take, we've got this line going through P, we've got X and Y, the points of intersection. Let's take another line, any old other line that's distinct from the one we've drawn. So, draw any other line. Draw any other line through P. So this one's going to intersecting C at points U and V. Alright, so we'll throw another line through here. That should be distinct from the original because I put this word other, so I guess that in my mind that means it's distinct. So not the same line. Here's points U and V. And it's not specified what we've written, but in this picture I'm going to add in 2 more lines. I'm going to add in this line XU and VY. Why did I do that? Because it gives us 2 triangles now. And in pretty much all of geometry, we work with triangles as often as we can. So we built these 2 triangles, and my claim is that these 2 angles right here are equal or congruent. Why is that?
Because of the arc.
Exactly. They're inscribed angles that both subtend the same arc, right? X V. Both of them. So now the inscribed angles XUV and the angle, what is that, VYX we'll call it? Vyx, both subtend to the same arc. I'll even tell you what the arc is. It's the arc XV. So they're the same angle. So in measure, angle XUV is equal to angle VYX. Okay, so we have that one. That's a harder observation to make. Here's an easier one. My claim is that these two angles are congruent. Why?
They're vertical.
Vertical angles. Also, angle XPU is equal to angle VPY because they are vertical angles. So what's true about these two triangles?
They're similar.
Why?
Angle, angle.
Angle, angle, right? By angle, angle. By angle, angle, we have triangle. Let's get the order here, right? These two angles match up at P, so we'll start with P on both of them. PUX is similar to triangle PYV. So hence, if they're similar, the ratios of the sides are the same, right? The sides are proportional in length. So here's two corresponding sides, PX and PV. Those correspond to each other, PX and PV. So that ratio should be the same as the ratio of any other two corresponding sides. And I'm going to go with PU and PY. And the reason I did this is actually to write this in a different way. The line XP and, the points XP and Y, they all correspond to one line, right? And the points U, P, and V, those all correspond to another line. So let's rearrange this. So we have points corresponding to one line on one side of the equation, points corresponding to another line on the other side of the equation. All I need to do is cross multiply here, and I'll have PX times PY is equal to PU times PV. And that's actually where I wanted to get with this. What does that say? Well, it's just this number, right? It says, okay, if I take this line P, this point P, and I draw the line through it, I end up with these 2 points. And it says if you take the product of these distances, the distance from P to X and P to Y, or P to U and P to V, just take that product for whatever reason, if you wanted to do that. It says it's always the same, right? In other words, it doesn't matter what line I draw. If I throw in another line here, and you take points, what letters haven't I using? W and Z, take the product PW and PZ, that's going to be the same. Right, so this product, which looks like it should depend heavily on the points of intersection with the circle, the fact that those are equal says it doesn't. It doesn't depend at all. It doesn't depend on the line that we draw, it's just based on the point P itself. And there's this independence, which is kind of interesting and kind of unexpected, that if you measure these distances, it actually doesn't depend on the line you choose. It's just the point P. But let's do case 2. And case 2 is basically the same thing. The observations are no harder. So I probably won't even write out all the details. So case 2, and this will be P outside. So we're looking at a picture like this. We'll put P over here. We did specify, so when P was inside, you really could choose any line that you wanted, but I did specify these lines have to intersect the circle. So I'm not allowed to choose lines that don't, but choose any 2 lines through P that do intersect the circle. Let's say that one and that one. X, Y, U, V. And we'll draw on two more segments to get at least inscribed angles. This segment and this segment. And once again, what do I have? I have these 2 angles here. Those are inscribed angles that both subtend the same arc, right? XU. So this is just a sketch. But angle PXU, that equals angle P, no. Why did I go PXU? Sorry, I've got everything wrong here. That's Y. Let's call it angle, let's call it PYU. I feel a little bit weird about choosing P instead of X because P lives outside the circle, but of course it's the same angle, so we'll call it PYU. That's the same as PVX. Because they subtend the same arc. And both of these triangles here, these are the 2 triangles I'm going to look at, PYU and PXV. Both of them use that angle right there. So also, angle P equals angle P. So by AA, this one's the easier case, you don't even have to invoke vertical angles. But by angle, triangle PYU is similar to triangle PVX. Right, and then it's exactly the same as before. So I won't even finish it now. And so we're actually proving something here. I haven't written down the theorem, but the theorem would be that if you take this product, if you take px times py and pu times pv, those are always the same. It doesn't matter what line you draw. So those distances, that product of distances or lengths of line segments, doesn't depend on the line. It just depends on the point P. So we'll state this. We'll say this is a theorem that we've technically already proven. And it is somewhat of an unexpected result. It's not mind-blowing or anything, but it is unexpected. So we've just shown this. We've really just proven this. Here's the theorem. That given a circle C, actually I won't even name the circle, we don't have to refer to it again. Given a circle and a point P not on the circle, choose an arbitrary line, any line that you want. Choose an arbitrary line through P, intersecting the circle at points X and Y. Intersecting the circle at points X and Y, then the quantity, so this product Px times Py doesn't depend on the line, right? It doesn't depend on the choice of line, it's independent of the choice of line, it depends only on P. And it certainly looks like it should depend on the line because that gives you X and Y, but it doesn't, as we've shown. This is independent of the line chosen. And it seems like it should depend on two different things, the point and the line, but it's just the point. So i.e. that is it depends only on P. So similar triangles are really interesting. They pop up all the time in geometry, and if you can, if you identify the fact that two triangles are similar, of course the congruence even better, but if you can identify they're similar, you can still say, or pull interesting information out of that, and the useful information. And they're so common that if you're working with geometric figures and you just draw in some extra lines and construct some triangles, more often than not you'll have stuff in there that's similar to each other. And we'll wrap up the section now with just some small things. Here's a short lemma. I'm not really going to use this to prove anything else, but we'll call it a lemma anyway. So suppose triangle ABC is a right triangle. Suppose this is a right triangle with hypotenuse AB. So we'll let this line segment CB, I've already told you it's, or sorry, CP, I've already told you what C is. C is a vertex on ABC. P will be the vertex that makes this line segment an altitude. So let CP be the altitude from C. Then triangle ACP is similar to triangle ABC, which is similar to triangle CBP. So here's what we have. I almost always draw my right angle triangles going this way. I suppose I could do that, but then I'd have to label my vertices clockwise, which feels wrong to me. So we'll do something else that feels wrong, which is drawing my right triangle facing that way. And then we've got A, B, C. Alright, so what does this want us to do? This wants us to draw an altitude from C. And it's called that line segment CP, so this point right here, that must be P. Because it's an altitude, what are these angles right here? Altitude means these intersect perpendicularly. And there's really two things that this theorem's claiming, is that if I do this, so I cut up this right angle triangle this way, this right triangle this way, then this triangle ACP is congruent, or not congruent, similar to ABC. Why? Well, remember, if you want to prove similarity, we have these conditions, right? We've got SSS, SAS, and just AA. And I think here AA suffices. This angle matches up with that angle. Right? Those are equal because they're right angles. And both of these triangles, APC and ABC, they both use that angle right there. Right? So they have two angles the same, they are similar. So here's our proof. Angle A equals angle A. And angle APC is 90 degrees, which equals angle ACB. And by angle, we're done. By angle, it follows that triangle ACB let's just make sure we match it up the right way. This side here, from A to P, that goes from angle A to the right angle, right? So that must be, the corresponding side over here must go from angle A to the right angle. That matches up with AC. So this would be triangle A. Oh wait. Yeah, I'm confusing myself. ACP, oh no, I've just gone backwards. Why don't we just identify the hypotenuse, that'll be a lot easier. AC, that's the hypotenuse of this triangle, right? So that matches up with the hypotenuse over here. AC matches up with AB, so AC would be AB. Let's see, there we go. I won't even prove the second part, it's completely analogous. Instead of using angle A, they still, these two triangles down here, this triangle is similar to the whole thing. You show that by saying, here's a right angle, matches up with this right angle, and angle B matches up with angle B. So similarly, triangle CBP is similar to triangle ABC. So sort of an interesting result is that if you draw this altitude in from the right angle in a right triangle, you always get three similar triangles. Yet these two are similar to each other, and they're both similar to the larger triangle. And I said I wasn't going to use this to prove anything, but what we'll do is we'll actually we'll write out a proof of the Pythagorean theorem. You might say, why? We've already looked at a proof, and yeah, that's true. But I also told you that the Pythagorean theorem probably has more proofs out there of it than anything else in existence. So why not talk about some of them? Because it's fun. Alternative proof of Pythagorean theorem. The one we talked about last time, the so-called rearrangement proof, the Pythagoreans almost certainly knew that one. I don't know if they would have known this one, but So again, we'll sketch it. I won't write out all the details. Just a really quick sketch. But what we'll do is we'll take a right triangle and label everything as we had before. A, B, C, and P. So let triangle ABC and point P be as above or before. I'm guessing your notes it would be above, so we'll call it above. And we'll label our lengths as we usually do. So Pythagorean theorem, A would correspond to, say, this side, BC, the side opposite angle A. So let A be length BC. Let B be the side opposite angle B, so that's length AC. And let C be the hypotenuse AB. By our lemma, ACP is congruent to ABC, or not congruent, similar, right? So by the lemma, triangle ACP is similar to triangle ABC. What does this imply? This implies that their side lengths are proportional, right? So this means that AP over AC, okay, this side matches up, corresponds. AP over AC, those two sides correspond. That equals the ratios of the other sides, but the other two sides I'm going to look at here are AC and AB. So the two hypotenuses. That's AC over AB. That takes just a moment of thought to identify corresponding sides, but yeah. AP and AC correspond by the ordering here of the triangles, and AC and AB correspond as well. Okay. Is that all right? Looking at proportional sides. Similarly, I'm going to come up with another ratio. So similarly, actually, I'm jumping ahead. Erase the word similarly, or let's just fit this in here. Let's replace this with some stuff. What's AP equal to? AP would just be AC squared over AB, right? And I think I have just enough room to fit this on this line. What's AC? AC is B squared, AB is C. So this means AP is B squared over C. All right, similarly, do that with the other two similar triangles. Do that with this triangle down here that we've already shown is similar to ABC. And you'll get another equation. So similarly, BP, go through the exact same work, you'll get that equals A squared over C. Now we're done. Can you see why? What if I add these two equations together? AP plus BP. Well, that would be B squared over C plus A squared over C. But what does AP plus BP equal? Yeah, AP plus BP is C, right? So finally, AP plus BP, that equals C. But by adding these two equations together, I also know it equals B squared over C plus A squared over C. So how do you get the Pythagorean theorem from here? Multiply both sides by C, right? Which means C squared, and I'll just write it in the opposite order, is A squared plus B squared. Kind of a cool proof. As long as you know that this altitude cuts your triangle into two similar pieces that are both similar to the larger one, then proof of the Pythagorean theorem is almost immediate. So a really cool theorem, or a really cool proof, though I guess the theorem's cool too. We've got 20 minutes, I don't think I need nearly that much time. So we'll just make one more observation. And I told you last class that I think the textbook definition of similar polygons is a little bit strange. So I'll give you a slightly different definition. But we defined similarity for triangles. Right? Triangles, thrigons. Right? What is similar for triangles? Our definition is three same angles, right? Three equal angles. Let me not say equal. That sounds like we're talking about equal arrows. Three same angles. And most of the section, most of the work here, most of the really involved proofs that we've done in this section, we're showing that this is equivalent to saying that you have three proportional sides. Right, so equivalent to three proportional sides. And both of these, either one of these, actually, either one of these sort of captures the spirit of what we wanted with similarity, which is similar triangles should have the same shape, right? We didn't care about the size anymore, you can be scaled, but, so either one implies same shape, right? Because that's what similar should mean. But what about for larger polygons, right? What about for n-gons in general? Say with n at least as big as 4. What should similar mean here? Again, I want similar to encompass this idea of my two polygons have the same shape. We've already seen that for, say, here's a very simple example. Take any of the two rectangles with different aspect ratios. So here's a nice square, all 4 right angles. And here's a rectangle with a much higher aspect ratio, all 4 right angles. clearly those don't have the same shape, right? They shouldn't be what we think of as being similar, similar quadrilaterals. So it's not enough to just say similar. In this case, we'll define this to be all angles are the same, because it doesn't really capture the idea. So having 4 of the same angles is not enough. What if we then say, okay, what if we specify we have 4 proportional sides? Well, here's something like that. Here's a, I'll just draw my rectangle on its side. If I want to define similar to meaning that you have 4 proportional sides, one thing I could do is imagine this is sort of made of a folded over straw or something. You'll notice this shape isn't rigid. I can sort of pinch it on the sides here and squeeze it together. The side lengths would stay the same, but I get much more obtuse angles there. I'm not intending to change the side lengths here. Let's pretend lambda is 1. But again, there's 2 quadrilaterals where now the sides are proportional to each other. They're actually equal to each other, but they're not similar at all, because these angles are very different now. They're not the same shape. But it turns out it's enough that if you specify both of these things, if you have equal angles and proportional sides, then you will encompass this idea of having the same shape. So this is how we'll define similarity for n-gons in general, is you need to define both of these things to happen. So similar in this case is going to be corresponding sides are equal, or sorry, corresponding angles are equal, and corresponding sides are proportional. And if you do this, now when you talk about similar n-gons, if you make this definition, well, now that encompasses, yeah, they have the same shape. So this is the more general definition for similarity that you need to apply to sort of larger n-gons. You can make this definition for triangles as well, but in mathematics we try not to overdefine things. And it turns out here you can go with the weaker definition for triangles as we saw. If you specify either one of these things are true, all the angles are the same or all sides proportional, then the other one is automatically true. So we don't make this additional definition for triangles because you don't need to. It was a lot of work to show that you don't need to, but you don't need to. Any questions? All right, so we'll end with just a fact. I won't prove it because it's hard to prove. But here's a fact. Maybe, why not? Why call it a fact? It's a theorem. I just won't provide a proof. But here's a theorem. Let P and Q be 2 similar polygons. Let these be similar polygons with scale factor lambda. And so what I mean by that is that here I'm going to make up some notation, but it's obvious what the notation implies. So what I mean by this is that P is congruent, or you can think of it as being equal to if you want. It's the same as just being lambda times Q. Right, again, I'm making up notation there, but obviously this means that the corresponding sides of P are just lambda times the corresponding sides of Q. Okay. Then, case of P. From our notation we've used earlier in the class, what do you think case of P? represents?
Area of P.
Yeah, so this would be area of P. How does this relate to the area of Q? Well, what if you take squares? Or not even squares, just take rectangles. So let's say this is Q, with side lengths R and S. And this is P, with side lengths lambda R, lambda S. What's the area of Q in this case? It's a rectangle, so it'd just be R times S, right? What about P? What's the area of P? Again, it's a rectangle, so it'd just be lambda R times lambda S. Or I can factor out the lambdas, and I have lambda squared times RS. Well, RS was the area of Q, so this is lambda squared times Q. Or sorry, case of Q. So there's a proof for rectangles. For rectangles in particular, if you have similar rectangles, this is the relationship between their areas. It's one way you can think of this is if you take the ratio of the areas is the square of the scale factor. Well, it turns out that's true in general. For any similar polygons, it doesn't matter how weird they look, how many sides you have, it's always lambda squared times the area of the other. Proving this is difficult. Easiest way is probably to invoke some sort of calculus. The reason I talked about squares here is because now it's not too hard to convince yourself that, okay, take two similar polygons. Maybe I'll go with some similar pentagons here. What's one way you could find the area of this pentagon? Well, one thing you could do is you could just cover it. You could cover it with a bunch of squares. Right? Cover it with a whole bunch of squares. Add up the area of those squares, and that would give you approximately the area of the pentagon. Right? You've got a little bit of overhang, a little bit of overestimates, but how could you make that approximation better? Again, think calculus. Make the squares really small, right? So if you make these squares smaller and smaller and smaller, you will get, and you add up the area of all those squares, you get exactly the area, right? Because the overhang becomes less and less and less and less, and the error tends to 0. Well, come over here, cover this with squares in the exact same pattern, just scaled by a factor of lambda, because the scale factor here is lambda. So cover this with squares in the exact same pattern. And what's the area over here going to be? Well, the area of these squares is lambda squared times the area of those squares. Again, shrink them to 0. These will always be lambda squared times the area of those. But shrink them to 0, and you'll get that the area, or the error of the area, is shrinking to 0. So you'd formalize all this stuff. You'd write up a proof like that using calculus, using limits and everything. We're not going to bother, but that would be the spirit of the proof, is overlapping things with squares that are shrinking to 0 and adding up those areas. Does that make sense? There's a lot of places in geometry where calculus is really useful. Somewhat surprisingly. and obviously not a tool that the ancient geometers would have had. They didn't know anything about calculus. So anyway, we'll stop 5 minutes early today, and have a great weekend, guys.